Okay, we are continuing with our light unit crash course where we go through things really quickly, but I just exposed you to the material. Just like the last video, while you're watching this, I would like you to write down 5 things you learn or things that you find interesting or fascinating. And then you'll put those facts into the LMS quiz at the end of the video. All right, we are now on page 248 where it says mirrors. Mirrors. Have you ever bounced a ball against a wall? Light reflects off different surfaces in much the same way that a ball bounces. When light shines at an angle onto a smooth surface, the light bounces off at an equal angle in the opposite direction. Mirrors reflect light in this way. When light shines on a rough or bumpy surface, the reflected light goes in many different directions. Some surfaces, such as paper, look smooth. However, if you use a microscope to look at a piece of paper, you will see that its surface is rough. So light that reflects off the paper will go in many directions. So I'm going to go to our PowerPoint, and the first thing we're going to talk about is a mirror. Rough surfaces such as paper and snow reflect light, but they do not make good mirrors. Mirror surfaces are shiny and smooth. A mirror is any surface that can reflect light to form an image or picture of an object. A mirror with a flat surface is called a plane mirror. Most common mirrors, like your bathroom mirror, are plane mirrors. A plane mirror shows an image that looks exactly like the real object. The only difference is that the image is reversed. So, hold on for a second. I need to fix my PowerPoint, so I can do that real quick. Like I do in class when I go through stuff really, really fast and make sure head spin. Okay. So we are up to mirrors. So the plane mirror is the mirror you use in your bathroom or your bedroom. You look at it, it's an exact reflection of what you look like, except it is reversed. And that is the only difference. So that is a plane mirror, P-L-A-N-E. And here is an example of a plane mirror. Okay, look at the top of page 249. You may have noticed that the front of an ambulance has the word ambulance written backwards. This is so a person driving a car in front of an ambulance can look in the rearview mirror and read the word clearly. This lets the person quickly know to get out of the way. Some mirrors are curved. Curved mirrors change the way an image looks. They can make the image look larger or smaller than the object really is. You may have seen curved mirrors at a fair or an amusement park. The amount of curve can vary. Some mirrors curve a lot. Often, others have a curve so small that it may not even be noticeable. A mirror that is concave curves inward. These mirrors reflect light toward a point in front of the mirror. If you stand close to a concave mirror, your image is magnified or made larger. Many women and men use concave mirrors when they put on makeup or shave. Sometimes it's just called a makeup mirror. This kind of mirror allows them to see better detail. Some telescopes use concave mirrors. These mirrors help faraway objects look bigger. A mirror that is convex curves outward. These mirrors reflect light that spreads outward. Images seen in a convex mirror look smaller than the objects really are. You can use a convex mirror to help you see a large area. Many stores use convex mirrors to watch for shoplifters, and automobile side mirrors are convex mirrors. Okay, I'm going to show you first my slide of concave mirror. It curves inward, okay, and concave mirrors give us a magnified image. And we have the convex mirror that curves outward, and that will give us a smaller image. All right, so this video that I'm going to show you is a pretty cool video. I'm not going to show you all of it, but some of it. He asks you to go and get a large spoon from your silverware drawer. So if you want to do that real quick, pause the video and get a spoon, because the spoon is a really good way to study concave and convex. Okay, here we go.
Hi friends, Do you know that mirrors are of different types? Plane mirror and curved or spherical mirrors. Spherical mirrors can be further divided into concave mirror and convex mirror. So there are three types of mirrors: plane, concave and convex. In fact, I have all these three mirrors on this wall here for you. I'm going to go and stand in front of each of these mirrors and let's see what do we observe. If I stand in front of the first mirror, I appear to be the same height. If I stand in front of the second mirror, oops, I appear to be inverted.
Upside down.
Now if I move close to the mirror, I appear to be magnified. Now if I stand in front of the third mirror, I appear to be shorter. Can you guess the type of mirror for each of these? That's right. The first mirror is a plane mirror. The second mirror is a concave mirror. And the third mirror is a convex mirror. Let's talk about the three mirrors. A plane mirror has a plane or flat surface. And I'm sure you must have noticed that when you stand in front of a plane mirror, you appear to be the same height. Now let's look at concave and convex mirrors. These mirrors are curved mirrors. And a very simple way to understand them is using a spoon. So I'd like you to pause the video right here and go and get a spoon. And it'll be great if you can get a large and shiny spoon. So are you ready with your spoon? A concave mirror is curved inwards. So if you look at this side of the spoon, can you see it is curved inwards just like a concave mirror? Now hold the spoon like this and look at yourself in the spoon. What do you observe? You appear to be inverted and smaller in size or diminished. Now if you bring the spoon really close to yourself, you can see that you are looking magnified. But an easier way to do this is to hold an object like a pencil and get it really close to the mirror. Now you can clearly see the magnification. So a concave mirror is the only mirror that can produce an inverted image in this position or a magnified image. A convex mirror is the opposite of a concave mirror. So if we flip the spoon, here we have a convex mirror. Now if you look at yourself on the convex side of the spoon, what do you notice? You appear to be smaller, but your image is now straight or upright. And no matter where you move the spoon, the image in a convex mirror is always diminished and upright. So this was our quick recap on the three mirrors. More details on spherical mirrors coming up later in the video. But first let me ask you, which types of mirrors are you using in your daily lives? I'm using all three types of mirrors every day. If you don't believe me, I'll be showing you some clippings from my daily life. And you need to be a detective and identify the type of mirror. Is it a plane mirror, concave mirror, or a convex mirror? Are you ready? Let's start. In the morning, when I shave, which type of mirror am I using? The shaving mirror is a concave mirror. The face in the mirror is magnified. If I flip this mirror, there's a plane mirror behind this. Can you see the difference in magnification between the plane mirror and the concave mirror? When I comb my hair, which type of mirror am I using? This mirror has a flat surface. It's a plane mirror. When I leave the house and go down in the elevator, which mirror does the elevator have? It's a plane mirror. To save time, I can actually comb my hair on the way down. While driving the car, I use the two mirrors, the rear view mirror and the side mirror. Which types of mirrors are these two mirrors? That's right. The rear view mirror and the side mirror are examples of convex mirrors because they give a greater field of view. There are mirrors kept at road intersections so that you can see the vehicles coming from the other side. Which type of mirror are these? That's right, convex mirrors. So as you can see, I'm using all three types of mirrors every day: plane, concave and convex mirrors. Spherical.
Okay, that is all we're going to watch of that video. And let's go back to our PowerPoint. So plane mirrors, concave mirrors, and convex mirrors. And I loved how he showed how we use each one of those in our daily lives. All right, now let's look at page 250, Light and Technology. An X-ray machine is just one tool that has been developed from the study of light. There are also many other inventions that make use of light. What do some telescopes, lasers, and cameras have in common? They use mirrors and lenses to change the direction of light. A lens is a piece of glass or other transparent object that refracts light and produces an image. Telescopes help people see things that are far away, such as planets and stars. Some telescopes are small, others are huge. The Subaru telescope located in Hawaii weighs 555 tons. That is more than the total weight of 56 buses. Regardless of size, however, all telescopes use mirrors or lenses, or both, to collect and bring light to a point or focus. A reflecting telescope uses a concave mirror to gather and focus light. The light is reflected to the eyepiece lens, which magnifies the object. A refracting telescope usually uses two convex lenses. One lens gathers the light, and the other magnifies the image. Okay, let's go to a short video about telescopes. Give you a little bit more information.
One of my friends is asking me about telescopes and how they work.
So how do telescopes work, Adam?
Well, as you know, the main function of a telescope is to form enlarged images of objects that are far away. When we see a distant object with our bare eyes, it seems to be very small, while it is actually very big. Look, Omar, look at the moon. It is about a quarter of the size of the Earth. But because it is so far, it looks tiny. Take another example. Look at our car. Down on the street, it looks so small, although it is actually large enough to take Muhammad, Salma, you and me inside.
So why does it look small then, Adam?
Okay, let me tell you why. You know, of course, that our eyes see any objects by the light that this object reflects, right? Now, this light gathers and forms an image of the object on a small point inside the human eye. Telescopes do pretty much the same job. They gather the light bouncing off objects, but they form an enlarged image of it. How do they do that? At the front tip of the telescope, there is a large curved lens that collects the light reflected by the distant object and focuses it on a point inside the telescope. At the other end of the telescope, another small curved lens enlarges this focused light and displays it inside the eye. Because the light is focused, the image covers a larger area inside the eye, and we see it larger.
I see. So it's all about lenses then?
Not really. Some telescopes depend on curved mirrors. So now we have two kinds of telescopes: refraction telescopes and reflection telescopes.
What's the difference, Adam?
Refraction telescopes use a big lens at the front to collect light, while reflection telescopes use a curved mirror to do the same. Both types use eye lenses to form the image at the end. Reflection telescopes use a series of curved mirrors to collect the light. The light comes from the front, then a curved mirror reflects it to deliver it to another mirror, which reflects inside the eye. Most astronomers nowadays use reflection telescopes because the images produced by refraction telescopes do not give good quality colors. This color distortion happens because of small differences in the wavelength of color components of light when focused. This means that forming images with crisp colors requires huge lenses, but with time they become less effective and form distorted images. Mirrors are not like lenses because we can support them from behind to make them more effective and durable. The diameter of a glass mirror could reach 5 meters. It is coated with a layer of aluminum that reflects more than 95% of the light that falls on it. The larger the telescope, the larger its ability to magnify the light, and therefore the final image is brighter. There are several kinds of telescopes. There are simple or handheld telescopes, like the ones pirates used. There are also binoculars, which are actually two telescopes combined so that you see three-dimensional objects. Then you have the giant telescopes that are used in observatories, and orbit space telescopes, which extract images that are free of the distorting effects caused by Earth's atmosphere.
Orbit space telescopes? I thought that telescopes can only be used on Earth.
No, Amar. There are many giant telescopes that are installed on satellites. They give us information about stars and dust clouds in space. We could never have obtained such information from visual images. You see, there are telescopes that work with ultraviolet rays and are particularly useful for studying hot stars and glowing gas clouds. There are also infrared telescopes, which locate cooler dust clouds that do not emit light.
Oh Allah, what a fabulous scene. Wow, what's that? There's a monster coming at us. Run, Adam, run! Help!
Okay, that was just a little short video to introduce you a little bit more to telescopes. The reflecting telescope uses a concave mirror to gather and focus light, which was reflected to the eyepiece, which was demonstrated in the video. Then there's the refracting telescope that uses two convex lenses. One lens gathers light and the other magnifies the image. And as was said in the video, most telescopes used by scientists today are reflecting telescopes. All right, now please look at page 251 in your book. Cameras also use mirrors and lenses. There are many kinds of cameras, though, and each works in a slightly different way. A single lens reflex camera uses a mirror, a lens, and a prism. Lasers use mirrors to produce a thin beam of light that is very powerful. This beam of light is only one color. Inside a laser tube is a medium for the light to travel through. The medium can be a gas, a liquid, or a solid. And there is a picture of a ruby-colored laser on this page. At the end of each tube is a mirror. As light travels back and forth through the medium, the mirrors reflect it. One of the mirrors in the laser is semi-transparent. It reflects some light and lets some light pass through. Some of the light leaks out of the tube through the mirror and produces the beam of light. The color of the laser depends on the type of medium that is used. Ruby lasers have a solid ruby rod inside the laser. These lasers give off red light. Other lasers with red light may use a gas instead of a ruby. Different gases can cause lasers to give off blue light or green light. Lasers can be found almost anywhere. DVD players and CD players use lasers to read the content of a disc. Checkout scanners in many grocery stores and other stores use lasers to read the barcodes. When you go to the store and you take the thing you're buying over the laser and it goes beep, it's the laser reading the information off of the code. Doctors sometimes use lasers to perform delicate surgery or to look inside a patient's body. Some lasers cut cheese into fancy shapes. Others are powerful enough to cut through steel. Okay, now you are going to turn in your book to page 254 to a part of the chapter that I think is absolutely fascinating, and it's called the electromagnetic spectrum. It's an arrangement of electromagnetic waves according to their wavelengths. Even though we can see light waves, there are many kinds of waves that we cannot see. Like light, these waves are electromagnetic waves. but light is the only type that is visible to the human eye. Electromagnetic waves come from the sun and other sources. So you see on this chart right here, this little tiny section of the electromagnetic spectrum is the visible light that we can see. There are many other waves that we cannot see. All electromagnetic waves travel at the same speed, but they have different wavelengths and frequencies. Remember, we've learned about those two terms. Electromagnetic waves can be arranged in the order of their wavelengths. This arrangement is called the electromagnetic spectrum. Light waves have a specific wavelength and frequency. Other electromagnetic waves have shorter wavelengths and higher frequencies, or longer wavelengths and lower frequencies. So, first we talk about the waves with longer wavelengths. The first one is the radio wave. Radio waves are the longest kind of electromagnetic wave. Radio waves carry energy that is used for radio and television broadcasting. Sound information is added to radio waves by changing either the frequency or the amplitude of the wave. Antennas pick up radio waves from the air and send them through wires to the radio. The radio then changes the radio waves into sound. Radio waves are not used just for radios, though. Garage door openers and baby monitors also use radio waves. Even the wildlife tracking collars use them. The waves help track the location of wild animals. And if you look at the picture of that key, a remote car key uses radio waves. We cannot see radio waves because they have too long of a wavelength for us to see, but we use them in our regular daily lives. The next wave on the spectrum is the microwave. Should sound familiar. Microwaves have a shorter wavelength than radio waves do. Microwave ovens use microwaves to cook and reheat food. Cell phones also use microwaves. Some radar uses microwaves to detect the speed and location of objects. A police officer shoots microwaves from a radar gun. When a car passes, the waves reflect off of it and return to the radar gun. The rate at which the waves returns helps the police officer know how fast the car was going. If your parents have ever gotten stuck in one of the police speed traps where they used a radar gun and they pull you over because you were speeding, that is actually microwaves they are using. Radar is also used to direct airplanes, to locate ships at sea, and to track weather systems as well. The next part of the electromagnetic spectrum is infrared waves. In the electromagnetic spectrum, infrared waves are between microwaves and visible light. The heat that you feel from the sun or a fire is from infrared waves. Infrared rays transfer thermal energy better than any other kind of electromagnetic wave. We call this kind of heat transfer radiant heat. We learned about that a long time ago. All objects give off at least some infrared waves. Warmer things, such as people or animals, give off more infrared waves than cooler things, such as buildings. Our eyes cannot see infrared waves, but some equipment can detect them. Police officers can use this equipment to track criminals at night. And there's an infrared image of a cat. You also use infrared waves each time you use a remote control. You do not see the infrared waves that go between the remote control and the television, but they are there. Each time you press a button, the remote sends an infrared wave that the television picks up. Some binoculars and cameras can change infrared waves into light that you can see. Satellites and space telescopes may use infrared cameras. Pictures from these cameras help a scientist see things even when there is no visible light. So, then we get to the part of the electromagnetic spectrum that we can see. And this is our visible spectrum that we've already talked about. Now we are on page, see what my page number is, 256, shorter wavelengths. Other waves in the electromagnetic spectrum have wavelengths that are shorter than that of light. Because the waves are shorter, the frequencies are higher. These waves are also invisible to humans. The next part of the electromagnetic spectrum is ultraviolet light, which might sound familiar. The wavelengths of ultraviolet rays are just a little shorter than those of violet light. Ultraviolet rays cause some materials to glow. Some things, such as glow-in-the-dark balls, can absorb the rays and give off visible light. In normal light, we do not see the glowing colors of the ball, but in the darkness, the ball will glow. Ultraviolet rays can help keep people healthy. Some kinds of bacteria are harmful if found in water or food. Ultraviolet light can detect some kinds of bacteria, so it is used to test food areas. The rays can even kill some kinds of bacteria. Some hospitals use the rays to sterilize their equipment. Small amounts of ultraviolet rays help your skin cells produce vitamin D. That's why they tell you to go out and get fresh air and sunshine, because the sunlight helps your body make vitamin D naturally. But too much of these ultraviolet rays can cause wrinkles, sunburn, skin damage, and at the worst, skin cancer. You should always be careful when outside. Most of these waves are absorbed by the ozone layer of the atmosphere. However, rays from the sun can reach the earth even on cloudy days. Using a sunscreen lotion with a high sun protection factor, SPF, can protect you from getting too much ultraviolet light. So this is why we should wear sunscreen. Because if you don't wear sunscreen, your skin will absorb too much ultraviolet light, and you get sunburn. As you get older, you get wrinkles, skin damage, and at the worst, you can get skin cancer. So, you're going to look at the next page, page 257. Then we come to X-rays. They should sound familiar too. X-rays are a type of ultraviolet light. They carry a lot of energy and can pass through a variety of materials. X-rays occur naturally. Many things in space, such as stars and comets, give off X-rays. X-rays can also be produced by machines. Marie Curie took some of the first X-ray machines to the front lines to help save lives. Doctors use X-rays to see the bones inside someone's body. X-rays can pass through skin and muscles, but are absorbed by bones. The places where the X-rays are absorbed the most show up as bright spots on the X-ray film. Too much exposure to X-rays can cause cancer. That is why dentists and doctors use special coverings to protect the part of the body that are not being X-rayed. Early X-ray scientists, as well as those who used X-rays, did not know of these dangers. In fact, Marie Curie eventually died from overexposure to X-rays. So if you go to a dentist and they take X-rays of your teeth, they will put that large, kind of heavy bib on you. That is to block the X-rays from getting to the rest of your body. If I broke my foot, I had to go and get an X-ray for my foot. They gave me something to cover the other part of me so that I did not absorb those X-rays. So too many X-rays can be harmful, so you need to be very careful about that. And doctors and dentists know that, and they take precautions every time they use an X-ray machine. You've probably experienced that at least once. For a long time, X-rays have been used on pieces of art. Historians can use X-rays to see whether a painting was painted on top of an earlier one. Sometimes an old canvas was reused in order to save money. At other times, the painting on top might be a forgery, a painting made to look as though someone else painted it. So in the little caption there, it says, the X-ray of the painting shows details of another painting under the finished work. And then at the top caption, the doctor is examining an X-ray of a person's lungs. X-rays can also be used in industry and engineering. Some factories use X-rays to inspect packaged goods as they move along production lines. Engineers can X-ray structures made of steel or concrete. The X-rays show if there are any tiny cracks, which is important. Airports use X-rays for security and to check baggage. So when you put your suitcase under that little security thing, when it's inside that little box, they're using an X-ray so they can see what's inside of it to make sure you don't have anything harmful or dangerous. The last kind of rays on the electromagnetic spectrum are the gamma rays, and we are now on page 258. The shortest waves in the electromagnetic spectrum are called gamma rays. The sun and other stars produce gamma rays. Gamma rays are very powerful and can cause serious illnesses. When used in a controlled situation, though, gamma rays can be very helpful. They can treat some kinds of cancer. The rays can also be used to sterilize bandages and other medical equipment in a process called irradiation. Irradiation can help some foods stay fresh longer if gamma rays are used to kill bacteria in the foods. God has given people the command to learn about electromagnetic energy as well as the minds to do so. Scientists and engineers have gained much knowledge about the electromagnetic spectrum. They have learned to use nearly the entire spectrum to benefit people. As we learn how people, plants, and animals use these energies of light, we can glorify God for his infinite wisdom and creativity. So that is the electromagnetic spectrum. And breaking it down one more time, you've got the radio waves. They are the longest waves. They're used for radio, television, garage door openers, and baby monitors. You've got microwaves, used for cooking, also used in your cell phone and in radar. You've got infrared rays. The heat you feel from the sun or a fire is from infrared waves. Warm things give off more infrared rays than cool things. The remote control that you use in your home uses infrared rays. The visible light spectrum that we've already talked about, from violet light to red light. Then we have ultraviolet light, ultraviolet rays. So they cause some things to glow. If you have things that are glow in the dark, they are able to reflect ultraviolet rays. They can detect bacteria on food. They can sterilize hospital equipment. They can also cause wrinkles, sunburn, skin damage, and skin cancer, which is why it is recommended that we wear sunscreen if we're going to be exposed for a long time to the sun. The next kind of rays is X-rays. X-rays are used by doctors to see inside someone's body. Airports use them in security. And too much exposure to X-rays will cause cancer, and that's why doctors and dentists use protective gear for themselves and for us when they use X-rays. Then we have the gamma rays. They're very powerful. They can cause serious illness, but if used correctly, they can fight cancer, they can sterilize medical equipment, and they can help food to stay fresh longer. All right, I have one more video for you, and it is about the electromagnetic spectrum, reviewing what we've just introduced. And it's by NASA, which is cool.
Something surrounds you, bombards you, some of which you can't see, touch, or even feel. Every day, everywhere you go. It is odorless and tasteless, yet you use it and depend on it every hour of every day. Without it, the world you know could not exist. What is it? Electromagnetic radiation. These waves spread across a spectrum from very short gamma rays to X-rays, ultraviolet rays, visible light waves, even longer infrared waves, microwaves, to radio waves which can measure longer than a mountain range. This spectrum is the foundation of the information age and of our modern world. Your radio, remote control, text message, television, microwave oven, even a doctor's X-ray, all depend on waves within the electromagnetic spectrum. Electromagnetic waves, or EM waves, are similar to ocean waves in that both are energy waves. They transmit energy. EM waves are produced by the vibration of charged particles and have electrical and magnetic properties. But unlike ocean waves that require water, EM waves travel through the vacuum of space at the constant speed of light. EM waves have crests and troughs like ocean waves. The distance between crests is the wavelength. While some EM wavelengths are very long and are measured in meters, many are tiny and are measured in billionths of a meter, nanometers. The number of these crests that pass a given point within 1 second is described as the frequency of the wave. One wave, or cycle, per second is called a hertz. Long EM waves, such as radio waves, have the lowest frequency and carry less energy. Adding energy increases the frequency of the wave and makes the wavelength shorter. Gamma rays are the shortest, highest energy waves in the spectrum. So, as you sit watching TV, not only are there visible light waves from the TV striking your eyes, but also radio waves transmitting from a nearby station, and microwaves carrying cell phone calls and text messages, and waves from your neighbor's Wi-Fi, and GPS units in the cars driving by. There is a chaos of waves from all across the spectrum passing through your room right now. With all these waves around you, how can you possibly watch your TV show? Similar to tuning a radio to a specific radio station, our eyes are tuned to a specific region of the EM spectrum and can detect energy with wavelengths from 400 to 700 nanometers, the visible light region of the spectrum. Objects appear to have color because EM waves interact with their molecules. Some wavelengths in the visible spectrum are reflected, and other wavelengths are absorbed. This leaf looks green because EM waves interact with the chlorophyll molecules. Waves between 492 and 577 nanometers in length are reflected, and our eye interprets this as the leaf being green. Our eyes see the leaf as green, but cannot tell us anything about how the leaf reflects ultraviolet, microwave, or infrared waves. To learn more about the world around us, scientists and engineers have devised ways to enable us to see beyond that sliver of the EM spectrum called visible light. Data from multiple wavelengths help scientists study all kinds of amazing phenomena on Earth, from seasonal change to specific habitats. Everything around us emits, reflects, and absorbs EM radiation differently based on its composition. A graph showing these interactions across a region of the EM spectrum is called a spectral signature. Characteristic patterns, like fingerprints within the spectra, allow astronomers to identify an object's chemical composition and to determine such physical properties as temperature and density. NASA's Spitzer Space Telescope observed the presence of water and organic molecules in a galaxy 3.2 billion light-years away. Viewing our Sun in multiple wavelengths with the SOHO satellite allows scientists to study and understand sunspots that are associated with solar flares and eruptions harmful to satellites, astronauts, and communications here on Earth. We are constantly learning more about our world and universe by taking advantage of the unique information contained in the different waves across the EM spectrum.
Okay, so the electromagnetic spectrum is a fascinating thing, and one of the reasons I like that video is how it shows all of those waves going through the living room at the same time. Well, that's happening all around you all the time, every day. It's because our eyes can only see the visible light spectrum, that we don't see the radio waves and the microwaves and the infrared rays. So I find the electromagnetic spectrum to be very interesting, very fascinating, and how we use all those different rays in different ways to help people. So, like I told you in the history videos, this is just a little teeny tiny short review, like a little overview of light. Very short, not much detail. If you're interested, do some research and find out more about all of these topics. Now, as I told you at the beginning, the LMS quiz, all you're going to do is put in 5 things that you learned from the video or that you found fascinating or interesting. Okay, so you should have been writing these down while you were watching the video. This shows me A, that you watched the video, and B, that you were paying attention and listening and you actually picked up some information from it. Okay, this is our last science video. Can you believe it? 5th grade science comes to an end. I've enjoyed teaching you science this year, and I've enjoyed making these videos. I wish we were together in person. I hope that you have learned a lot through our science videos for the past few months. Bye, guys.